SwayamPrabha. Digital India. Educated India.
And then you have your actuator, which is physically in the analog domain, and plant analog domain. Sensors may be analog to digital, depending upon whatever is a sensor interface. And then you typically have this setup for any mechatronic system. And you may have feedback in some cases, like you may be missing the feedback also. The sensor feedback may not be there. Okay, some systems are like that. But in general, you have this feedback and closed loop control happening in a typical, especially high fidelity mechatronics kind of a system. Okay, and then we saw some basics of what happens when the signal is sampled, especially when you take the sensor signal, which is analog domain, and you sample it, and you want to kind of represent it in the digital domain. And now we are looking at how the signal is faithfully representing what it is supposed to be. The contents of the signal in some sense are preserved when you sample it. Okay, that's what we are discussing. And for that, the main theorem is about the Shannon sampling theorem. Okay, so a couple of these questions you should be keeping in mind and seek answers for. How do we kind of say that the samples are true representation of the original signal? Or how do you recover the signal back from the samples? Okay, are there any method? Is there any method, or under what conditions we can do this complete recovery back? And how is it applicable to our case? Like say, this PWM is going to the motor as a sampled signal. So now you may have a little bit of a clarity needed here. See, this PWM is itself has this switching signal, right? It is going positive and zero at very high frequency. When we say sampled, so what for all our practical purposes, what we consider this PWM signal when implemented on our motor is that it is giving some average voltage to your motor. Okay, and that average voltage is now given as a sampled form. Okay, so this average is one value, and after some sampling time, it is changing its value. Okay, that's how we can visualize this or look at this. Otherwise, if you say, okay, my PWM signal itself is sampled, but it is at high frequency, and if I want to consider that also into account in analysis, then it's a different story. Okay, what we are assuming here is, especially for PWM signal. See, otherwise, if there is an analog interface to control motor, then absolutely no problem that your analog signal is at some value. During the sampling instance, it remains constant value. Okay, and then in the next sampling instance, is a different value. So what is this effect of this kind of a way of actuator receiving these signals in this kind of a step form? Okay, every sampling time the step value changes. So we'll look at that in due course. Okay, so we started off with these fundamentals of sampling, and this is an analogy one can use, or physical thinking can be done based on this. All the concepts that we see later can be easily understood if we connect it to this kind of analogy. Because this gives you some kind of a visual kind of a way to think about stuff, and we'll see formally as we go mathematically how things work out. But we will not derive the equation. We kind of use some of these sampling theorems and the reconstruction part and things like that. So as we saw, if you sample when this arrow is let me get a pointer, arrow is at a point before the 180-degree position. Okay, so if arrow is here and the next arrow position, if it is before 180-degree position, we can see that, okay, we can faithfully kind of see the wheel direction and velocity as well. Now you can see that, see, if I sample it here and it completes one rotation and goes beyond, and again I take a second sample, that is also a possibility. Okay, but that will indicate you a speed which is not reality. Okay, although the direction is same. Okay, you can see that, the arrow is pointing here, it completes one rotation and comes here, and I take that as a sample. So even in that case, the direction is proper, but the speed information is not proper. Further, if I say, okay, it starts from here, completes one rotation, completes second rotation, and again comes to the same that position. Okay, that is also one possibility. But that will give you the same speed when it is reproduced, but actual speed has happened with the two rotations in between. So this is information that is getting in some way. Okay, so how to see that in the frequency domain is slowly that we'll look at that. So the frequency domain representation would give you all these kind of possibilities that are there for such a sample signal. Okay, so how that happens, we'll see in a while. Okay, so same thing extended now to actual signal and its time samples here. Okay, so you can see that here some other kind of a frequency sine wave is coming up. Okay, so you have original sine wave which is going at very high frequency, and then when you are sampling it, your low frequency sine wave is coming up in the signal. Okay, so if you see, this problem is similar to this wheel kind of a problem. Okay, so the frequency at which you are observing the wheel to be moving is much slower. Okay, and in the opposite direction for this particular kind of a case. So like that, you'll have this frequency of the sinusoid is much lower, and its phase is also not in line with the phase of this original kind of a signal. Okay, so that is how one can kind of connect these two things to kind of think physically what might happen to your signal. Okay, now this is more kind of a formal mathematical kind of a representation of what we are talking now, generalized to a signal. Okay, so this is a signal f of t, which is in general like a evolving signal with some frequency content. And what we are interested in is a signal for which the frequency contents are typically in kind of such a signal. So frequency contents are obtained by using the Fourier transform of the signal, and the numerical way of doing that is fast Fourier transforms. And those fast Fourier transforms would give you this this kind of a plot of we saw some example signal here. This signal. Okay, so this is the original signal, and this is its fast Fourier transform. Okay, and in the FFT you can see that the signal has a content which is some frequency here and some small frequency at one end of here. Okay, so beyond that there are hardly any frequency content. So this signal is kind of band limited to frequency of about say 35 or that kind of a value. Okay, so like that we can say that this signal typically is represented, this triangle has, or this kind of a straight line has no really great meaning here. I mean, it just to signify that the signal has some content in this domain. It may be one kind of a single line or multiple lines. We don't know what the contents are. But typically the signal is generally represented in this kind of a form. Okay, so actually if you want to really see what is this, then you need to take FFT. But just to kind of for the purpose of the discussions, people would represent the signal saying that okay, well, it has some content here. They will represent these contents in this kind of a triangle form. And now the question arises is that, okay, suppose I sample this signal and get these white dots. These are the samples which are recorded in my computer. Okay, this is coming up as a vector array in my computer. Then what is the frequency content of such a signal? Okay, so these frequencies can have multiple kind of values here. Okay, how that is happening is based on some mathematics of Fourier transform. So this signal is represented for the mathematical kind of a transforms, Fourier transform for sample signal. The sample signal needs to be represented in terms of some kind of a math, and that is a mathematical representation of the sample signal direct data function. And then when you take a Fourier transform of this signal and do some kind of a mathematical manipulations, you would end up with this sample signal Fourier transform. Okay. Now for this sample signal Fourier transform, you can see that you can see that this f is a Fourier transform of original signal in the analog domain. Okay. So this sampled Fourier transform is represented in terms of some kind of a form of original signal Fourier transform. So f of t is original signal and its Fourier transform is f of j omega. So this is f here. Okay, so f of j omega is this Fourier transform, but now when it is sampled, there is some kind of a scaling that is happening here. 1 over t is some kind of a scaling factor coming, and then there is a summation of multiple copies of this f of j omega, which are replicated at frequency k omega s. Okay, so for example, if k is equal to 0 value, you can see that this is nothing but f of j omega here. Okay, so that is one part. So k is equal to 1, then it is shifted by frequency omega s, and as omega s is the sampling frequency 2 pi over t. Okay. So that's how one can interpret this, and with this, if I want to plot it here, say for k is equal to 0, this will simply replicate here as this signal. F of j omega is this value, and this will simply replicate here at f of for k is equal to 0. Okay, and then for k is equal to 1, it will be replicated at omega s value. So I need to kind of find where is the omega s here. And at that axis, I need to again replicate the signal as it is from here to f of where k is equal to 1, where omega is equal to omega s value. So this is what will come like this here. Okay. So when the signal is like this, its sampled form will look something of this sort. Here there is one time there is a replication, then there is a second replication here. Then there is a third replication at a minus. So you see, if it is minus infinity to infinity k value, so it is keeping on replicating everywhere. That is the main crux of this sampling theorem. That it says that your signal in the frequency domain will get mirror itself at multiple omega s values. Okay, and that has some sense. I was talking about even after rotation of one complete rotation, you'll have the frequency can be same. Okay, some kind of a sense of that information is coming here. Your signal is getting replicated at multiple omega s values, and that's how your samples can be visualized. So your samples are just discrete data points. Okay. If I say the frequency contents of those discrete data points, they'll be represented in this kind of form. Okay, so now if I start changing this omega 0, so my frequency content or omega s, okay, I decrease the sampling frequency. Okay, so what you can imagine now, this sample is first replica is coming here. You can see the scaling also, 1 over t scaling is happening here. And now this part is going to come more closer to this. Okay, as I start decreasing omega s. Okay, so as omega s decreases, this will start shifting. Okay, in omega axis here. and keeping omega 0 same, if I am decreasing omega s, then at some point, like this omega s over 2, these two will start touching each other. Okay, so when omega 0 becomes omega s over 2, I still have these two samples, these signals, they are touching each other. So if you see, these signals here still have the same kind of a form, like a triangle form that it was there for the analog signal. Okay, it is still preserved here. But once you see that my omega s decreases below certain value, okay, which is 2 times omega 0 kind of a value, then my signals will start interacting with each other, and you see that there is a summation of these things. Okay, so when they start overlapping, you need to actually sum them up in the frequency domain. This is the frequency domain of the sample. You sum them up in the frequency domain, and they'll start now missing the information. So this original signal was something of this sort, and the new signal has now lost that information here. Okay, new signal has beyond this frequency lost some part of the information is getting lost. Okay, so that is what is called aliasing, and that is why the signal has to have sampling enough frequency enough so that we don't see this loss of a signal. Okay, so any questions so far? This is what is the crux of Shannon sampling theorem. Actually, one part which is that the signal should be sampled at least twice its largest frequency content, so that it is represented in its full form in samples. Okay.
So in the strain gauge Fourier transform, there weren't any repeating triangles, right?
Right. So Fourier transform would give you a signal. Let's see, which is only up to the first part of the frequency contains. Okay, only up to the limit here. See, okay, these are done like a digital Fourier transforms. Okay, so this is done in a way that your maximum frequency here depends upon what is the sampling frequency. So you assume that the signal has whatever aliasing that has happened already, and beyond that, whatever is the signal content, it is produced only up to omega s over 2. Omega s over 2 will be the frequency here. So if you have sampled this signal at frequency, I think in this case we sampled it at a frequency of 1 millisecond, or 1 millisecond was 1 kilohertz. So this maximum value here on this frequency axis can go only up to 500. And beyond that, we cannot represent, because it's going to be a replica of the same thing is assumed. It will not come as a part of the numerical FFT method of getting the Fourier transform. So this understanding is implied here that okay, this part is going to get repeated beyond this 500 hertz frequency that is there for the omega s over 2 value.
Perfect, got it.
Yeah. I mean, one can kind of set up your plots in a way that you want to kind of see them as plotted like that, but FFT algorithm does not by itself really do that. Okay. So this is the main part here. So you see that when we take samples, although these samples are looking as this kind of points here as some impulses, in the frequency domain they are not seen as impulses. Okay, that is the main thing that you should not confuse about. Okay, they are seen as a continuous signal here. Okay, when we do numerically some stuff, there is a different story. Don't worry about that part. But because it is sampled here, it produces samples here also. No, that is not correct. Okay, it produces this actually. This is like an analog kind of a signal here. In some sense, this is analog means it's a continuous signal here. Okay, this is in the frequency domain. So see, these are different domains of thinking. Okay, so frequency domain like is different from time domain thinking. There is a transform that is happening in between. Okay, so once you say, okay, this is the samples that I am representing here in the time domain, that doesn't mean that in frequency domain also I will have only the samples. No, that is not correct. That is what main thing one should not fall in that trap. Okay. So clear this part, like, okay, that this is how, like, the signals get mingled up or mixed up and gets messed up. Okay, when we start sampling it with a lower sampling frequency. And now one can see that, okay, see if I have my signal in the form of that rotation. Suppose we take the wheel rotation example, then omega 0 value is what is of my interest. So there is one kind of a, say, what omega 0 is the frequency of or the speed of rotation. Okay, so that value will be represented here as omega 0 signal. And now if I sample it at multiple kind of different frequencies, one can see that if the sampling is not fast enough, then I'll see this omega 0 coming up here. If I measure from here, see this part is Fs here, or Fs of Fs replicated at so this is my 0 basically. Okay, so when k is equal to 0. Okay, and now this is omega s value up here. Now omega s it will get replicated here again, and omega 0 from this side will come up here. Okay, so this frequency is what I am going to see as a first frequency when I start replaying that signal. Okay, and this frequency is now, you can see that it is less than omega s over 2. Okay, so this is a much lesser frequency than original frequency omega 0 that I had here. Okay, that is what is going to be seen in this signal, which is not sampled enough actually. That's how one can start thinking about this. And okay, so like that one can see whatever that rotation way of doing things can be seen now in the formal mathematical kind of representations here. Okay. Now Shannon has proposed further reconstruction. Now the question is, okay, you say that, okay, if I sample it faster than twice the frequency contents of the signal can be completely reconstructed. I mean, the signal contents are preserved. So now the question is, how do I reconstruct this signal back? Okay, and there is this other derivation, mathematical derivation. This both of the derivation, like the how this formula comes up from basic Fourier transforms, and like how this expression comes up by considering the filtered version of that signal. Okay, so you filter this signal by using, so your sample signal is like having now many such kind of replicas here. We want only first replica, which is at 0 frequency replica. That value, that is what we need to kind of preserve. And so we filter this signal using this ideal filter, which is a flat filter here with a scaling t, so that we cancel out this 1 over t by this scaling factor, and then we can reproduce this signal back. Okay, that is how one can think of reproduction of the signal in the frequency domain, and by using those kind of fundamentals, one can work out what is happening correspondingly in time domain, and that's where you get this formula for time domain representation of the signal. Now, so this is how the signal can be reconstructed from the samples. Now let's understand what is it this part is doing here. Okay, so these are the samples. This is FSKT is a samples of the sample of the signal, and then each of the sample is multiplied by some kind of a function here. Okay, and then they are all added up together is what gives you this reconstructed signal back. Okay, so and then this particular function is of the form sine theta upon theta. Okay, so we'll see what is this function looks like and things like that. Okay, so let's kind of see that now. So reconstruction part is having this kind of a formula, what we have seen, and now we'll see how one can construct the samples back, the signal back from the samples. Okay, so say these are the samples here. Okay, so these are different colored kind of things are representing samples at t, 2t, 3t, 4t, things like that. Now this function, as saying that it is sine theta upon theta kind of a function, and if you know from your mathematics, this function will have if you see sine theta upon theta limit as theta tends to 0, its limit is actually 1. Okay, so this function is called sometimes sinc function. Okay, sinc theta. Okay, and it has some representation of this kind. Okay, so if you plot it against theta, when theta takes value of pi, then this function is going to go to 0 again. Okay, so at 0 value, although this sine theta upon theta and the limit as theta tends to 0 is 1, and when sine theta is equal to pi, this will take value 0, and so on and so forth for integer multiple of pi values. Okay, that's what is going to happen here. Okay, and this is a way the amplitude will go on reducing, because as theta increases, the overall value of this coming as 1 over theta, so the amplitude is 1 over theta, which gets reduced for a sine function. Okay, so this is how this function evolves in theta. Okay, now theta in our case here is actually pi t minus kt upon t. Okay, now what does it mean? Suppose suppose say k is equal to 0, then this is like pi t over t. Okay, okay, and then this theta would take this value pi t over t, and this function will have now variation coming in time. Okay, so now instead of theta, it will be coming as a time function here. Okay, and when the time becomes equal to capital T, okay, is pi t, then theta becomes equal to pi. So this value will be equal to capital T. Okay, you can see that, right? Say k is equal to 0. Okay, so this term is not there, and now your t becomes like a capital T value. Then theta becomes pi, and we know that at theta is equal to pi, this function takes value 0. Okay, so when it gets kind of multiplied to this, it has this scaling factor here, additional scaling factor is f of kt. So every sample will scale this signal. Okay, so this, suppose this is a sample. So instead of this one value at whatever this value. Okay, other thing. Okay, let's see what happens when theta is equal to 0. When theta is equal to 0 part here, this is the theta is equal to 0 position. Okay, which is this y-axis for this function plot. At that point, t becomes equal to kt. That means, for each sample, this function is going to get placed here. Okay, at a sample value such that this one matches or gets scaled by the sample value itself. Okay, so I'll have this say for say k is equal to 1. If I want to put this here, then t will be equal to capital T here. So at that point my theta is going to be 0. So this value 1 will get scaled by this f of kt factor, and then it will come here. So this signal, if I start now drawing, and I know from here, if I go 1t apart, I will hit theta is equal to pi value. Okay, so this signal is going to come first as like this. Okay, so for k is equal to 1 value, this function is going to look like this here. Okay, and it will have some kind of a variation. Okay, is this part clear? Any questions about this? So we are just considering one case, k is equal to 1, and then seeing how this mathematical form or this function is represented as for k is equal to 1. Okay, and then we need to consider that now that for k is equal to minus infinity to infinity ideally, but we don't have samples before 0, so we consider samples starting from 0. and first sample here is maybe 0. Then how this signal is evolving, okay, how this construction is seen, okay. So
Sir, not clear. Why did we choose this form of function? Because there will be interference between the consecutive sample reconstruction, right?
Right. So it's not interference, but this. So say if I now do it for k is equal to 2, I'll get another kind of a signal which is sketched up here, like that. Okay. So this might produce 2 signal.
So this is
uh,
still an approximation of a original signal, right?
So I'm just kind of considering now k is equal to 1, k is equal to 2 only. I have to consider k is equal to minus infinity to infinity, then it is giving me complete signal. It's not an approximation. It is, see, if I limit myself to some few values of k alone, then it will be approximation. If I consider all the values of k, okay, all the samples that are possible for the signal to be considered, then it is not an approximation.
But essentially, you're still fitting it between the points, right? It's just that if you have lot of points, then it might look like an original signal.
No. It's not that. So look. So it's not that you need to have in between points also. No. That is not what I am talking about. I am talking about that it has all the samples are there. Okay. So right now I am talking a little bit of a from the mathematical perspective, saying that okay, if I have all the samples known, okay, from t is equal to 0 to t is equal to infinity, or k is equal to 0 to k is equal to infinity, all the samples I have available, or beyond certain point my signal is 0, for example, and I know that okay, all the samples are there, then I'll be able to kind of reproduce my signal back completely.
So my doubt is, if you evaluate this function at suppose t by 2, somewhere in the middle point, more or less there will be a slight error, right?
No, that's what I'm saying. So we'll come to that. Like say for example, between these two values, okay, t and 2t, you have this signal coming up right now and this signal coming up right now. So they are getting added and they'll produce some kind of a form here. Okay, then if you see, if I consider next sample k is equal to 2 sample or k is equal to 3 sample, okay, I have this signal coming up. So this is also contributing to, this part is also contributing to something between t and 2t. Okay, like that every sample, okay, say I consider this blue part. Okay, blue part has also something to contribute between t to 2t. Then I consider next part. Okay, like that if I consider all these parts, they'll have something to contribute between this t to 2t. And that's what is a beauty and problem both for I'll tell you why beauty and why problem. Okay, so this Shannon reconstruction considers all the samples, and every sample has some representation between these two values.
Okay, so if
I go from 2t to 3t again, I can see that the previous samples also are contributing something, and future samples are also contributing something.
Okay, ideally k is going from minus infinity to infinity, right. But if I put it in a numerical software, then it depends on how many samples I'm choosing for the summation, right?
Right. That's where you will have, if you're doing the numerics anytime, you'll have some approximation. But it will be much better construction than saying that okay, I'm just holding the sample here and I'm waiting till the next sample to happen, and again I'm changing that value and holding it here again like that. It's much better approximation than that. Okay, so or if you have this some kind of some linear kind of interpolation between the two samples, that is other kind of a construction that can be possible. But that is not still a Shannon reconstruction, because the signal is not smooth, it's not getting reproduced exactly what it was. But even if I use say for this sample I use two future values and two past values, okay, and reconstruct that itself with the Shannon kind of a formula, it will give me much better kind of approximation. It's a smooth function that is going to come up like that. Okay, your signal is actually in some sense getting reproduced, in a very smooth manner. And if k is equal to infinity, then it will be like exactly replaced. But now the problem is that for any reconstruction here, I need a future values, all the future values. And in our mechatronics system or real-time control system, it's impossible to get future values beforehand, right? Because your feedback is happening, because based on the feedback, the future values will come. Okay, so you cannot have the channel reconstruction possibility in the mechatronics control systems at all. So this is a very important aspect of this, that okay, whatever reconstruction that we need to have, they need to be causal in nature. They should be using only the previous samples values. Okay, they should not be using like your future values, which we don't know. Okay, so the standard reconstruction is not a causal reconstruction. It is using all the future values to construct the signal pack. That's where like the problem is. Okay, so that's why you cannot use the standard reconstruction or this ideal kind of a reproduction of the signal for mechatronics or control kind of a domain system. Okay, but then the question is where it is useful. Anybody knows where this channel reconstruction could be useful in some way? Okay, this is useful for the cases of like you have heard about like you're digitally representing a sound. Okay, so your songs or like anything sound representation in the digital way, if it is done, all your future and past samples are available, right? For any kind of the sound to be played back again. Okay, so these high fidelity sound systems, they would use this kind of future information about the samples to do some kind of a reconstruction based on the future values of the samples to get the quality of sound produced in the same way as it was recorded. Okay, this is not analog recording, this is like a digital recording of a signal, and you want to produce really to the very close extent to the analog kind of reproduce that sound again. You can use these kind of concepts. Okay, so communication industry would use this in some way. Okay, so your digital high fidelity sound representation, or reproduction of the sound again, they can use this channel reconstruction. But for our control systems, this is not feasible to do. Okay, so what we do is we hold the values in the register. Remember, you have this duty register in which once you put the value, it will not change by itself till the time you put another value there, and you will have a chance to put another value only when you kind of complete one sampling time instance and come back again and you put other value there. So till that time the value will be held constant. Okay, so the way you are reconstructing the signal is basically holding this signal constant from here to the t to the 2t value. Okay, then it is changed to this value, and again that value will be held constant. Then it's changed to this red value, and again that red value will be held constant. And again then it will be changed to blue value, it will be held constant. This is how in some kind of this step form you represent that signal as a reconstructed signal. Okay, especially for implementation on a motor or actuator. So this is how one can think of Shannon sampling theorem and make use of that for sampling the signals in a way to make sure that the contents are preserved to its best form. It's just to think about what should be the function here, which when multiplied by this f of kt, and this should be function of t minus kt, such that I'll now produce my this steppy function, steppy form here.
So for the steppy function, we can use the rectangle function.
Yes. So this is what we're talking about, this stability function here. Okay, and it is already here. Okay. So this is a frequency domain. Oh, sorry, don't confuse here. It is a frequency domain kind of a representation. Okay. So maybe my like some writing here is little confusing. I'll just so this is called zero order hole. I'll just correct this and repost the slides again probably. This is called zero order hole, or you may note down like this ideal reconstruction written here is not a correct thing. Okay, just delete this part. Ideal reconstruction. This is not ideal reconstruction at all. Okay, ideal reconstruction will be this part, where you have this T and the rectangular window coming up here. This is ideal reconstruction. This is a different part. This is like that rectangle function that Siddharth was talking about. So instead of this this sync function here, this rectangular function will be coming up here. Okay. So this function, when represented in the same form f of kt, this function t minus kt would give you actually this reconstructing signal back, which is called zero order hole. So the zero order hole you'll find in MATLAB. Some places people have used this in the digital domain to A to D or D to A conversion. Okay, so the systems we want to transform from analog domain to digital domain, like you will be asked, okay, whether they should use bilinear transforms or they should use zero order hole kind of a form, or what kind of a form that is to be used. That time, you understand that okay, zero order form means zero order hole means I'm holding this value till the next sampling instance. If this is happening, and under this scenario, if I want to see what my system is responding, then that digital system conversion from analog to digital domain is what is based on this zero order hole kind of a form. Okay, so if I reconstruct this signal back like this, okay, so we are not yet coming to the systems. We are just kind of talking about only the signal, how the signal is represented and reconstructed back from the samples. Okay, so what we saw so far is the signal getting sampled like this, and once this is sampled, what will happen to its frequency contents, and after that, if I want to reproduce the signal, what are the different ways I can reproduce the signal? And one of the ways is this Shannon reconstruction, reproduce it back completely, but that is a completely ideal case. We will not do that in the control systems domain. We'll rather do it this kind of a way. Okay, so now this is a way we are kind of reconstructing the signal into the sample. So if you see the sensor signals also, when they are sampled, and let me go to that slide. When they are sampled, this is the first slide that we are talking about. When they are sensor signals are sampled and put in the digital domain, their value is held constant till the next sample comes for the sensor. The way it happens for your duty cycle, the same way it will happen for the sensor value also. The sensor value will be held constant till the next sensor sample comes. Okay, again that value will be held constant till the next sensor sample comes. So all this kind of a reconstruction that is happening inside the domain, although we are kind of representing these values as a discrete time values only and processing them for whatever purposes, they are actually, if you see, they are held constant over the two samples. Okay. And then that holding constant over the two samples has much more kind of a effect when it is implemented on the actuator. Okay, it doesn't matter too much when you kind of just process those values here, but it has much more implication when it is implemented on the actuator. And how that happens, that we'll see in a minute.